Okay, welcome back. Today I'm planning to continue discussing three-dimensional field theories, and I'm going to get to gauge theories today, and we'll start discussing some ideas about duality. But before we get to duality and these more abstract ideas, it will be very helpful to start from the O2 model. This is one particular example of the class of models that we discussed yesterday that I call DON models. So the O2 model has a few properties that are very interesting and they're very important for experiments. So I'm going to discuss some of these a little bit unknown or sometimes unfamiliar issues. But before we start, maybe if there are any questions about yesterday that are important to discuss before we start. Are there any questions about yesterday? Any? Okay. So I'll start. The method of attack here is going to be the same as what we did yesterday. This echo is bothering me. So now it's better. So the method of studying this model is going to be the same as what we did yesterday. We'll try to understand the semi-classical regimes, and we'll argue that there must be a phase transition, and then I'll tell you about what is the conjecture about the nature of this phase transition, and we'll discuss some of the properties of the phases that appear in this model. Now, this model is also called that comes under several names. One name for So we'll think about it as the Euclidean field theory. You can also think about it through this weak rotation as a Minkowskian theory, and I'll do that soon. There's a Minkowski version of this model. I mean a lattice construction, a Hamiltonian quantum phase transition zero temperature construction of this model. But it's just that you know, this model is called in the literature sometimes the O2 model, sometimes the O2 Wilson-Fisher model, but people sometimes call it also the XY model. That's another name for the same thing. It's a name that appears for some historical reasons. In the literature, basically the reason is that it's an O2 model, so there are two coordinates, phi 1 and phi 2, and this reminds us a little bit of a plane, where the coordinates are x and y. And the O2 is the symmetry of the model, because phi is like a vector, so you can act on a vector with an O2 transformation. Okay, so at some audience participation, at very, very large m squared, which is positive, how many vacua have we got? 1, and it's gapped, right? And the O2 symmetry is unbroken. The O2 is unbroken. We have one gapped vacuum, and the excitation, what is the simplest excitation that you can make out of the vacuum? It's phi, right? So just take phi, act on, in the Minkowski interpretation, act with phi on the vacuum. There you go, you have a particle which is an O2 vector, and it's massive. Okay. What about huge negative m squared? No. No. S1. Why is it not the Higgs mechanism? There are no gauge fields. In the Higgs mechanism, there is no degeneracy of the vacuum. There is only one vacuum. Here, there is an actual S1 worth of vacua, S1 worth of vacua, and the low energy theory has a massless field, so it's a gapless phase. It's a gapless phase. Condensed matter theory is called this phase the superfluid phase. This is what's called superfluidity in condensed matter. That's called the superfluid phase. And to describe the effective theory in this phase, we write phi equals absolute value of phi. So we think about phi as a complex instead of thinking about it as a vector, we think about phi 1 plus I phi 2. Okay, being a little sloppy. Vector is the same complex numbers, and then there is some phase sigma. And the effective field theory in this vacuum is just d sigma squared with some coefficient. In particle physics, this coefficient is called the pion decay constant. In condensed matter, this is called the stiffness coefficient, the D3x. Okay, so the effective filter is just a compact boson, a compact real boson. Sigma is identified with sigma plus 2 pi since it's the phase of some complex number. So it's a compact, it's just an Ambu-Goldstone boson for S1. So it's a S1 Ambu-Goldstone boson. Yeah?
How does the T-duality of the compact scalar manifest in superfluid?
T-duality is a 1 plus 1 dimensional, it's a 2-dimensional thing. Here we're talking about 2 plus 1 dimensions. But this is a great question, since you'll see that I'll soon discuss T-duality in 2 plus 1 dimensions. It just doesn't take the scalar to itself, it takes it to something else. You'll see soon what it's gonna be. Okay, so we have so the degrees of freedom in this phase is a single compact pseudoscalar, to be precise. And there is people believe, and this has been shown with a huge degree of confidence on the lattice, there is a single phase transition between these two phases. In condensed matter, this is called the insulating phase. This is called the insulator. This is called the superfluid. So this describes the superfluid. Sort of the superfluid insulator transition, and there is a single phase transition here, which is the O2 fixed point. This is again an abstract conformal field theory about which we know a lot of numerical data. We know the scaling dimensions of phi, we know the scaling dimension of phi squared to many digits. These are some constants of nature again. And okay, so if you take helium-3, there is at some temperature helium-3 becomes a superfluid. That's the critical point. And people measured many parameters experimentally. Okay, now there's something about this that is very important to discuss in preparation to what the gentleman remarked, the T-duality, because there will be some version of T-duality soon. So there is a slightly annoying thing about the superfluid phase that causes a lot of confusion. So let's think about the superfluid phase. In the superfluid phase, this is the action. And sigma is identified with sigma plus 2 pi. There is an excitation, or I should call it a pseudo-excitation. Let's call it a pseudo-excitation. In this phase, which receives a lot of attention in the literature because it appears experimentally and it's going to be very important in T-duality soon. So the excitation is the following. You take space. This is our R2. Now I'm thinking about it as a Minkowskian person. Okay? So we think about space and we have time, and we just try to construct an excitation which is static and has some energy, a classical excitation. So we basically take sigma to run such that it goes from 0 to 2 pi. So sigma goes to sigma plus 2 pi as we go around some circle in space. And of course, you cannot quite continue this configuration all the way to the origin. It's singular. So at the origin, there is something that people would call the core of this excitation. This excitation is called the vortex, the superfluid vortex. So this excitation is called in the literature the superfluid vortex. And it's been observed experimentally. So you cannot continue this configuration all the way to the origin because sigma is not going to be single valued. So instead, what you remember is that sigma is the phase of some complex scalar field. So the way to construct a solution that is regular at short distances near the core is to take the absolute value to 0 at the same time. So phi is some constant far away, but as phi goes to 0, as we converge to the core of the vortex, phi goes to 0 at the core. So phi, the absolute value of phi goes to 0 at the core, but very far away, here phi is a constant. And this constant is determined from m squared and lambda by minimizing the potential. So we find the constant by minimizing m squared phi squared plus lambda phi to the 4. And remember that this is negative. So you minimize this potential, you find the equilibrium value of the absolute value, and that's what it's going to be far away from the core. But the phase is going to rotate. And when you get close to the core, then the absolute value goes to 0, and you have a perfectly smooth solution at short distances. This describes some vorticity in the superfluid, and this has been observed experimentally. Yeah?
Why is it a pseudo-excitation as opposed to...
That's what I'm going to explain. This has been observed experimentally, this vortex. But if you think about it a little bit more deeply, you'll figure that there is a problem with it. Let's try to compute the energy. The energy of this excitation. The energy of this excitation comes from this action. It's the integral over space of d sigma squared, right? So near the core, there's something complicated. Phi, the absolute value goes to 0, and there is a complicated core structure. And there's no problem actually near the core. But at very long distances, this vorticity leads to a certain problem because this looks like r dr, r dr d theta, and there are some theta derivatives of sigma. So since there is one unit of vorticity, we can estimate this as the gradient theta of sigma squared. And this bidimensional analysis has to be multiplied by 1 over r squared. That's just the Laplacian. But this is basically 1, right? Because sigma goes around the circle with unit speed, so to speak, in angular velocity. So we get r dr r to the minus 2 at very large r. This is at a large r. And this is unfortunately logarithmically divergent as a function of the infrared cutoff. So that's why I called it a pseudo-excitation. These superfluid vortices don't actually exist in some sense. They cost infinite energy to be created. So to create a superfluid vortex, it costs infinite energy. So how come people observe it experimentally? Does anybody have an idea? Any ideas of how come this is observed experimentally? First of all, there is the finite volume, indeed. So, but more importantly, you can create a vortex, anti-vortex, and take them very far apart from each other. So let's think about it. Let's take a vortex and an anti-vortex and take them very far from each other. Let's say distance L. Okay? Now the total vorticity vanishes, so there's not going to be any infrared divergence. But there's going to be some leftover effect from this infrared divergence because we cannot take this L to be too large, because then it will cost a lot of energy to separate the vortex from the anti-vortex. So what is the energy that it would cost us? The energy that it would cost to separate these two vortex and anti-vortex distance L apart. Does anybody have a guess? What is the energy to separate it? We basically computed it just a second ago. Log of L, right? It's the same computation. You just estimate the contribution from the vorticity. So the energy to separate them far apart from each other is going to be like log of L. This comes from this leads to a force. What is the force? 1 over L. Is this force attractive or repulsive? Attractive. So we put a minus sign. Have you ever seen any force in 2 plus 1 dimensions that looks like minus 1 over L? Coulomb force. So this is where this seems similar to Coulomb force. And this is the beginning of duality, that you can think about these vortices as electric charges. Okay, so you see the first hints of duality. That the vortices are electric charges. And we have now a new interpretation for why we cannot have isolated vortices. because it doesn't satisfy the Gauss law. You cannot have one electric charge. You need to put total charge equals 0, right? So this is the beginning of, so just bear this in mind. Now, so the way that people observe them in the lab, of course, there are 3 ways in which you can observe it in the lab. You can have vortex anti-vortices which are separated. You can have finite volume. But most pragmatically, if you spin the superfluid, if you put the superfluid in a spinning bath, the angular momentum allows you to even create, I think, vortices in isolation. Yeah.
Just to be sure, which is the signature of the space?
Say again.
Which is the signature?
Well, I went back and forth. You can think about it as a Euclidean model if you like. But here I thought about it when I discussed vortices and forces. Of course, I thought about it in the Hilbert space interpretation.
Yes. But you said that there was a DC. I mean, there was a critical temperature.
Okay. Here I discussed the Euclidean O2 model, which has these phases and phase transition. That's interesting for some statistical classical systems. Then I discussed the Minkowskian version of the story, in which there are vortices, particles, and something that looks like a Coulomb force. There is a third point of view, which I mentioned in passing, which is that it's related to helium-3 at finite temperature. The way it goes there is the following. You start from a 3+1 dimensional fluid. You put it at finite temperature. Finite temperature is like a circle in the Minkowski interpretation. Sorry, finite temperature in the Minkowski interpretation is like a circle in the Euclidean interpretation. So you have now a 3+1 dimensional field theory, which is Euclidean on a circle. You reduce on the circle, you get some long distance description, which is that. So it arises from that story. That's how this model arises from the superfluid. Any other questions? Yeah, so I wanted to also, just for the perspective on the subject, to make contact with the discussion yesterday, I wanted to, in 5 minutes, tell you about a zero temperature phase transition. So zero temperature quantum phase transition, namely a Hamiltonian in two space dimensions, which whose ground state reproduces this phase transition in the exact same way that the transverse field Ising model yesterday gave an Isaac transition, that there is a gap, and then the gap closes, and you have a gapless zero temperature field theory, a gapless zero temperature Hamiltonian at infinite volume. So there is a model, a beautiful model that realizes this O2 thing, the superfluid insulator transition. That's called the boson-Hubbard model. It's called the boson-Hubbard model. It's a lattice model. So we start from a lattice again. It's a two-dimensional lattice. And now at each lattice site, so it's not quite like the lattice that we studied before. Remember that the lattice that we studied yesterday had a spin a half degree of freedom at each lattice site, and the spin a half could point anywhere it wanted with the sigma matrices. Now the rule of the game is a little different. Now we have bosons on the lattice, and the bosons can hop. So at each lattice site, you could have as many bosons as you like. The Hamiltonian is given by a sum over the lattice sites which are nearby, the neighboring lattice sites, and there is some coupling constant T. And then there is Bi dagger Bj plus Bj dagger Bi. And then there is some energy U. I'm going to explain what this whole thing means. Ni minus 1. I runs over all the sites, and Ij runs over all the neighboring sites. Ni is defined to be Bi dagger Bi. Okay, so by acting with B dagger I creates a boson at lattice site I. Okay? So the number of bosons at any lattice site could be anything, any integer. So this is the integer that measures how many bosons there are at lattice site I. These terms lead to some interactions between the lattice sites. What does this term do? It takes one boson away from lattice site J and puts it at lattice site I. Similarly, this takes one boson away from lattice site I and puts it at lattice site J. So basically it allows one boson to hop from here to here, or one boson can come from here to here. And how do you describe the wave function? The wave function is just a tensor product over all the lattice sites, where you say how many bosons you have at lattice site number 1, how many bosons you have at lattice site number 2. You just say this. And you do a superposition, of course, with arbitrary coefficients. Just a superposition of such states is the most general state in the Hilbert space. And B acts on this clearly by taking 1 from N and putting it in the nearby N. Am I being clear? Or not so much? Should I explain it again? Anybody? Yes or no? No.
Maybe just, okay, the model is clear, but what is the point of studying it, or what do you want?
You will see that this model exhibits the O2 phase transition at 0 temperature. I'm going to argue for it now. So this term basically allows the communication between the lattice sites. It allows two bosons to hop, to jump, to hop. And what does this do? If U is huge and positive, it forces the number of bosons to be at each lattice site 0 or 1. Okay? It would cost a lot of energy to have more than one boson at any given lattice site. Now, in such models, there is an important concept, which is called the filling fraction. I'm going to explain it now. It's very important for your general education. So there is an important concept which is called filling fraction, and it's what is filling fraction? So imagine it's a quantum mechanical model that you can put on the computer. Let's say that you have 100 lattice sites. This Hamiltonian has a conserved charge, a conserved total thing. What is the conserved number? The bosons, are you allowed to destroy bosons without creating them elsewhere? No. So the sum over Ni is conserved. It's a conserved integer. It commutes with the Hamiltonian. Okay? You can just verify it brute force at home, but it's obvious intuitively, since all the operators have an equal number of B's and B daggers. So when we diagonalize this Hilbert space, we diagonalize this Hamiltonian, we can diagonalize it sector by sector. We specify how many bosons there are in total on the lattice, okay? And then we diagonalize. So we specify, let's call, oh my God, let's call this N. We specify N and diagonalize. So you do it one by one. Very interestingly, this is a very important concept in condensed matter. The effective field theory description, or the effective physics, can strongly depend on the filling fraction, which is N divided by the number of lattice sites. This is an extremely important parameter in condensed matter. So if this is, let's say, smaller than 1, or half, let's say, you could have very different physics from when this is 1. And it's intuitively clear, because there is this term which restricts the number of bosons to be at most 1. So by having this parameter to be 1, it's clear that the physics is a little bit simpler. Okay? So we are going to take this to be 1 in our example. The claim is that when this is 1, it's called filling fraction 1. This model is in the O2 universality class. So the effective physics around that Hamiltonian, when the number of lattice sites goes to infinity and N goes to infinity, while the ratio is kept fixed, the effective description is the O2 model. How do we see that? Let's first take U to be very, very large. What happens when U over T is very, very large? What is the wave function? Well, we just put T to 0, so the lattice sites don't communicate anymore. Each lattice site is independent of any other lattice site, and you just have one boson at every lattice site because you have to have filling fraction 1. That's it. So the wave function of the ground state is just 1, 1, 1. One lattice site, one boson at each lattice site. And it's gapped. You can easily convince yourself that it's gapped, it's unique, gapped, unique, blah, blah. Okay? This would not be true if this was a half, for instance. Right? Then it would be much more complicated physics. In fact, we'll get to the model where this is a half later in the course, if I survive. So this is gapped, unique, and the O2 symmetry is unbroken. It's not spontaneously broken. On the other hand, the other limit is much more interesting, where T is huge. When T is huge, we remove the U constraint, essentially. And there is a and the bosons form a complicated state. And people have shown it's exactly solvable. This limit is exactly solvable because everything is quadratic. The whole model is not easily solvable because n is quadratic in the oscillators, and therefore n times n minus 1 is quartic in the oscillators. So the model is not linear. But in this limit, it becomes quadratic. The model becomes quadratic, and people have been able to solve it. And what they have shown is that the bosons form a pretty complicated state in which this is non-zero. The expectation value of the lowering operator is non-zero in the ground state. So this leads to spontaneous breaking of O2. So this is O2 is broken, you have a superfluid, and so that's the zero temperature construction of a superfluid. The bosons start hopping around the lattice, and there is no friction because U is 0. And they form a superfluid for some qualitative reason like that. I don't want to spend too much time explaining why, but there is a way to sort of, this might remind you of coherent states, so that's a hint. Coherent states are states where the oscillator, the raising operator or the lowering operator has a non-zero vev. So think about it a little bit at home. You can write the wave function in this limit using coherent states. Okay. So this is the O2 model.
Sorry, maybe a dumb question, but how does the O2 symmetry work here in this coming term? I mean, what does that?
You mean this conserved number?
No, the O2 symmetry in the case of the scalar field here that rotates the scalar field.
Yeah, it just multiplies by phase the B. So B is like the order parameter. B is analogous to our phi. Okay? Yeah? B is analogous to phi, and B dagger is analogous to phi dagger. Okay. Okay, so let's move on to, this was just a small example that I wanted to show you that there are constructions also for this model as zero temperature quantum phase transitions. Okay, let's discuss gauge theory now. Our first venture into something more complicated than just scalar fields. So, Maxwell theory. Let's discuss Maxwell theory in 2+1 dimensions. First of all, I'll do 5 minutes of classical Maxwell theory. I want to do 5 minutes of classical, and then we'll describe a little bit more the quantum story. So, classical Maxwell theory. What is classical Maxwell theory? It's just this equation. And the Bianchi identity. Well, these are just fancy unneeded derivatives. Okay, this is the classical Maxwell theory. And in classical Maxwell theory, you can put sources. You don't have to put sources, but you can put sources. Let's not put sources. Let's assume the J is 0. So in Maxwell theory in 3+1 dimensions, without sources, there are still interesting solutions, which are electromagnetic waves. Yeah. What is the situation in Maxwell in 2+1 dimensions? Are there electromagnetic waves? Does anybody know? Hmm? Hmm? Yeah, one polarization. So there are electromagnetic waves. There are electromagnetic waves, but just one polarization. So there are massless electromagnetic waves that move at the speed of light, and they have one polarization. That's the. What if we put a source, and let's say we put a charge, a static charge at 0, with some charge E? Well, I'm not going to discuss radiation, but we can write the electric field. So the electric field, as you already know, is 1 over R. And therefore, when you have a charge E and a charge minus E, they attract with force 1 over R. And the energy is therefore logarithmic in R. This is the energy. So, in 2+1 dimensions, it takes infinite energy to separate electric charges which are positive from negative ones. And this is unlike in 4 dimensions. In 4 dimensions, it takes finite energy to separate charges. Okay, so there is some sort of confinement. It's like weak confinement. It takes infinite energy to separate. Okay, this is the classical story. But already at this point, you can be struck that there is a very nice analogy to the compact scalar, not to the full O2 model, but just to the compact scalar phase. Right? Because in the compact scalar phase, we just had a sigma. How many degrees of freedom are in sigma? 1. One massless degree of freedom in sigma. And we had a similar force between the vortices. So indeed, this is the analog of T-duality in 2+1 dimensions. The analog of T-duality in 2+1 dimensions is that the Maxwell theory is entirely equivalent to an Ambu-Goldstone boson, which is compact. So Maxwell, this is both classically and quantum mechanically. It's an exact equivalence, which is actually, this is not the case for T-duality in 1+1 dimensions involves in an essential way these twisted sectors. Here, part of the duality you can see classically. So Maxwell is entirely equivalent with d sigma squared, where sigma is compact and massless. How do we prove that? Let me show you the proof. It's exactly like we prove T-duality in 1+1. We start from the Maxwell action, and we imagine doing the path integral over the gauge fields. And this is somewhat of an ST path integral because the action depends on f, which is a derivative of f. If we could only write it as an integral over f, we would be much happier because then it would be a Gaussian integral. So the idea is that we rewrite it as an integral over f, but we add another degree of freedom sigma, and we write the action as minus 1 over 2g squared f squared plus d sigma f mu nu, and we write an epsilon. There is some 2 pi here, and we write rho mu nu. So now, if you were to do the path integral over sigma first, then sigma would impose the Bianchi identity, and then you could write f as dA, and you would go back to the original theory. Okay, is that clear? So doing the path integral over sigma first takes you back to what you started from, which is an integral over f, which satisfies the Bianchi identity. On the other hand, doing the integral over f first, you find just the sigma up to some coefficients e to the power a. Well, E and then minus G squared d sigma squared up to some maybe a half or something like that. So that's how you derive the equivalence. So let's write this equivalence has many ingredients. Let me just spell them out. A great question. I hope somebody would ask this. So indeed, here it's not clear why I need sigma to be compact. If sigma is non-compact, then you can integrate it out, and it would impose the Bianchi identity. And you could then write f as dA. You would be happy. But there is something about U1 gauge theory which goes beyond the Bianchi identity, which is that the integrals of f over compact 2 cycles have to be 2 pi times integers. So the magnetic flux through closed cycles has to be quantized. This is the Dirac quantization condition. Remember that Dirac said that the flux through a sphere has to be quantized, right? Right? Yeah. No? Well, Dirac's argument is just that you don't have to talk about what's inside. Dirac's argument is just that if you have some flux of the magnetic field through some sphere, you can think about it as a monopole that's sitting inside, but you don't have to talk about it. It's a sphere. It's empty. It's just a flux through some sphere. Okay, let me rewind. Suppose you have the question is why is sigma compact? That's a question about topology. I'm going to try to give my best explanation. So if sigma were, okay, so first of all, you have to know something about U1 gauge theory. In U1 gauge theory, we have a Bianchi identity, which we can solve like this. Then you can ask, what is the integral of f over 2 cycles? If you are naive, you would use this formula, and you would say that this is the integral of dA over the 2 cycle, and this is the derivative of something, and therefore this vanishes. So the naive answer is that in U1, the flux of the field strength through any 2 cycle has to vanish because it's a total derivative. This answer is incorrect because we're not allowed to use the Stokes theorem here because A is not a well-defined one form. It's ambiguous. It undergoes gauge transformations. So the Stokes theorem says that integrals over one forms are the same as integrals over the boundary. Sorry, integrals of dW are the same as integrals over the boundary of W, right? That's Stokes' theorem. This theorem only applies if this is a well-defined form, a differential form. A is not a well-defined differential form because when you compare two patches, it doesn't undergo normal coordinate transformations. You're also allowed to do gauge transformations. So therefore, in electromagnetism, the flux of F through 2 cycles doesn't have to be 0. But it cannot be whatever you want. It has to be an integer. So this business with the gauge transformations doesn't allow you to do whatever you want. It allows you to have integer fluxes only.
So this with 2 cycles is it
Close 2 cycles. Close 2 cycles. Close 2 manifolds.
yeah, but in 3+1 dimensions?
No, that's true in any dimension. Any dimension. Is that more or less clear? Good. So the idea is that since this is not a well-defined one form, it doesn't have to vanish, but on the other hand, it cannot be whatever you want. It has to be an integer. So if sigma was just an ordinary non-compact scalar, it would have imposed these equations, and it would have imposed that A is a well-defined one form, and the integrals of F must vanish. We don't want that. That would not be U1 electromagnetism. To get U1 electromagnetism, you have to allow for the integrals of F to be integers. And for that reason, sigma needs to be compact. So this has to do with, you'll see in a second why, by the way. Okay? But is that more or less clear to everybody? This will be actually extremely important soon. So if there are any questions about it, let's discuss it now.
What would give the usual scale? What would give the usual scale by the same argument?
I don't understand. Yeah, if sigma was a non-compact scalar, it would have imposed this equation and this equation. So it would not allow for integer fluxes on closed 2 cycles. So it would not be U1 gauge theory. It would be what condensed matter theory is called non-compact gauge theory. In condensed matter literature, there is such a thing. They call it non-compact gauge theory. In fact, sometimes they call it non-compact U1 gauge theory, which is crazy because it doesn't even make sense. But in the condensed matter literature, they actually call it non-compact U1 gauge, which makes no sense grammatically, but that's how they call it. Non-compact U1 gauge theory is a gauge theory where A is a 1 form. So it cannot have non-trivial large gauge transformations, and all the fluxes vanish. But that's not what I'm interested in. I'm interested in actual U1 gauge theory. And for that, sigma needs to be compact. Yeah?
But that Z is like the number where the non-trivial bundle, non-trivial one bundle over the two. Is it?
Yes?
Okay. So it was never dimension because of this. Because I restrict the bundle, never dimension I am. And
I don't...
no,
Okay.
because my problem is that in higher dimension, for example, U1 bundle are trivial.
Not true. If there is a 2 cycle, they're non-trivial.
Because
They're-
I restrict and then a factory.
No, the U1 bundles are in general classified by the Chern classes.
Yes.
And they can be non-zero in any d-dimensional manifold depending on which cycles exist. If there are 2 cycles, 4 cycles, 6 cycles, there could be non-trivial U1 bundles. Any other questions? Yes?
Does the normalization matter for the 1 over 2 pi?
Yeah, the 1 over 2 pi's is everything is about the 1 over 2 pi's. The 2 pi, when I say U1 gauge theory, I mean that the allowed representations, charges, are integer. So the electric charge is an integer in my notation, and this 2 pi is important. The 2 pi tells you what gauge transformations are allowed. So what are the gauge transformations? The gauge transformations for A. This is the gauge transformations for A, right? So what is the distinction? Non-compact U1 gauge theory is that omega is just a function. Condensed matter theory is called non-compact gauge theory. Non-compact U1 is when omega is a function from space to R. From space to R. And since it's a function from space to R, it cannot have any non-trivial large gauge transformations. But what I'm interested in is the actual U1 gauge theory, in which W is a function from space to R mod Z, which is the same as S1. That's why I call it U1 gauge theory, because the space of gauge transformations is circle valued. Okay? And this allows some funny configurations with integer flux. Homework exercise, construct this thing on a torus. Take M2 to be a torus and construct explicitly a gauge bundle with this property. It's just magnetic flux through the torus. It's a straightforward exercise. Any questions? And you can also show that for the non-compact U1, you cannot construct such a bundle, and for the compact U1, you would be able to construct such a bundle. Any other questions? Okay, so now to the correspondence between sigma and the gauge theory. So far we just carefully defined what we mean by U1 gauge theory, right? So the correspondence is that on the sigma side, there is a clear U1 symmetry. That's the superfluid symmetry, the spontaneously broken U1. So the counterpart of that on the gauge theory side is just this. So this is the U1 symmetry of the superfluid, and this is the U1 symmetry of the gauge theory. This is a conserved. So Maxwell theory in 2 + 1 dimensions has a conserved U1. It might sound strange, but it's true. There is a conserved global symmetry, which is this given by this current. It's the Bianchi identity. In the literature, this is called U1 topological, because it has to do with the Bianchi identity. That's the name. U1 topological, or some people call it U1 magnetic, because it has to do with the Bianchi identity. These are two names. Okay, so this is one side of the correspondence. And here the 2 pi's are important because the fluxes of this are integer, so it's important to keep track of the 2 pi's so that both sides have integral fluxes on closed 2 manifolds. This is one side of the correspondence. And now comes a very important concept. Which is called monopole operators. This is another important thing about just free U1 gauge theory. We're so far discussing just free U1 gauge theory. So an important concept is the monopole operators. What are the monopole operators? So in a theory where there is a U1, yep.
That equation you're missing a dimension. That equation.
Yeah. Yeah, you're probably right.
This is mass scale.
Let me just try to see.
Because
Oh.
on this other side you are in a broken phase, so that is a scale.
Yeah, I want sigma to be dimensionless. That's the most convenient normalization for me. So indeed, I need to put this factor of the g squared. Yeah, you will see from this equation that if you were to integrate out f, then f would be given by g squared times d sigma. So g squared is the missing thing. Okay, so on this side of the story, there is a U1 symmetry, and it acts by taking sigma to sigma plus a constant, right? That's how the superfluid symmetry acts. On this side, what does it do? It doesn't do anything. So on this side, this is a topologically conserved current, and therefore it doesn't act on F mu. So U1 magnetic doesn't act on F mu. So on the sigma side, it's clear what it acts on. It acts on sigma. You could also say that it acts on e to the I sigma. If you constructed this operator e to the I sigma, it would act on I sigma very nicely, the superfluid broken symmetry. But what does it act on this side? So we're missing the dual of I sigma under this duality. What is the dual? What are the operators in Maxwell theory that transform under this U1? The answer is that these are the monopole operators. They are called monopole operators. And unlike in the sigma variables, where we can write them using the microscopic sigma variable, we can just write e to the I sigma. In this, these operators cannot be written using the gauge fields. They exist in the abstract in quantum field theory, but they cannot be written using gauge fields. So they cannot be written explicitly. So the funny thing about Maxwell theory that you have to remember is that while it's a straightforward Lagrangian, and we did many things with it already, it has local operators, genuine local operators, which cannot be written using the fields. Has anybody seen something like that before? Maybe in your studies you've seen something like that? Does anybody remember such an example from maybe elsewhere? Not you. Does anybody remember such an example from elsewhere? Have you ever seen local operators that cannot be written using the fields? Good. Twist fields. Any other examples? Winding operators. In general, in the condensed matter literature, as well as in the high energy literature, such operators are called disorder operators. That's the name. For some historical reasons that I don't want to go into. They are genuine local operators, but they cannot be written using the fundamental fields. Yet they exist. How they are defined? So we cannot write them using the elementary fields, but we can define them in an abstract way, or through the Maxwell theory. So what we give an algorithmic procedure to computing path integrals involving insertions of m or conjugate. So let me put an integer here. I can put an arbitrary integer here so that it's periodic under sigma going to sigma plus 2 pi. And now it has charge n under this u1. And then I would put an integer here. So all you have to do is to give me a prescription to compute correlation functions of monopole operators in U1 gauge theory. So even if you cannot give an explicit definition of these monopole operators, you have to give me some prescription of how to compute stuff. And the prescription is the following. So to compute such a correlation function, you, instead of studying R3, the path integral of R3, you remove the point x1, you remove the point x2, you remove the point x3. By remove, I mean you just cut it, and you make a small sphere around it. So there is a small sphere of size epsilon around each such point. And what you do is that you force the gauge field to have boundary conditions on the sphere so that it has this integer n. So the integral of the gauge field over ds2 that is centered around xi is going to be 2 pi times ni. No, 2 pi times in. No, xj, 2 pi times ij. Is the prescription clear? So, right. So let me rewind. For ordinary correlation functions in quantum field theory, the prescription is that we use weak constructions and Feynman diagrams. These operators are beyond that scope. They do not admit an expression using the elementary fields. You can go to the sigma variables, and in the sigma variables, they're completely straightforward. You can use weak constructions. But I want to give you a prescription already in the gauge field variables, just to impress it upon you. The prescription is that to compute such a correlation function, what do? You have to sum over all the gauge fields, right? With this action, with some insertions. But we don't know how to write these insertions. So what do? So instead of writing these insertions, we restrict the gauge fields that we integrate over. And we are only integrating now over gauge fields which are defined in R3 minus these points, minus x1 to xn. So we first remove these points from space. And secondly, there is a small sphere around each such point. Okay? And on this sphere, we put magnetic flux for the gauge field with the ij units. Around the sphere that is centered around xj, we put magnetic flux with ij units, where ij is this weird index that I introduced here. So instead of integrating over all the possible continuous gauge fields, we integrate over gauge fields with these boundary conditions. And this exactly reproduces what you would have got in the sigma language if you computed this using weak constructions in the sigma variable. So these operators exist. They cannot be written using elementary fields. And from this correspondence with the sigma, we can answer a very interesting question that has to do with dynamics, preparing us to some dynamics. So suppose you say, okay, I accept that these operators exist. So therefore, when I study U1 gauge theory, since these operators exist, I was told in quantum field theory that I can take any operator and integrate it and add it to the action. So what if I were to add to the action an integral over m plus m conjugate? So I need to add the complex conjugate, otherwise the action would not be real. But m conjugate is like m1 and m minus 1. Okay, 1 unit of flux and minus 1 unit of flux. And now we integrate them over the whole space. So this is also a valid action. But how can we ever analyze this action? Okay? This is the question. How can we ever analyze this action? Since M doesn't admit an expression using the elementary fields, it seems very hard. But to our savior is the sigma variable. Because we say, okay, I don't care. We just go to the sigma variables. And in sigma variables, everything is explicit. So let's pass to the sigma variables. We would get d3x, d sigma squared. That's from the kinetic term. And what do we replace m1 plus m bar 1 plus m by? So just that cosine. So let's suppose the coefficient is epsilon. So we had epsilon cosine of sigma. So the original Maxwell theory had the U1 magnetic symmetry, right? This theory has U1 magnetic symmetry, which is the Bianchi identity symmetry. Now this full theory does not have U1 magnetic anymore, because this transforms under U1 magnetic by a phase, by construction, right? And in the sigma variable, that's clear. That has a shift symmetry, but now there is a cosine. So there is no more shift symmetry. There is a potential. So this theory breaks U1, this breaks U1 magnetic. So that's how you break U1 magnetic symmetry. If you want to break this symmetry in 2 plus 1 dimensions, you have to add monopole operators to the action. This is called monopole proliferation. Sometimes people call it proliferation. Monopole proliferation. That's when you add monopoles to the action. Monopole proliferation. So we can do two things with monopoles. We can compute their expectation values, but that doesn't break the U1 magnetic symmetry. That's still a good thing to do. Or we can just add them to the action, and then we break the symmetry. And now we have a new model. And what is the physics of this model? Does it have a massless field? No. Why? Yeah, because there is a cosine. So the potential now is like this. Well, maybe no. This is the potential, right? And this is pi. This is pi. So there is one minimum now. So there is a minimum, and therefore there is a mass. So what's the mass? It's epsilon, basically. Up to some numerical coefficients, it's basically epsilon. So this is amazing. This is a mechanism to give a mass to what? To a gauge field. So the U1 Maxwell field can be given a mass by adding monopole operators. So that's a mechanism for Higgsing without adding additional fields. Yeah.
I don't understand the reason why we cannot write the monopole operator of that operator with 1 minus 1 in terms of the gauge fields. Does it mean that, for example, the equation of motion are not changed?
Or they are changed, of course. You can write the equations of motion in these variables, but in these variables, I don't know how to do that. Nobody knows. The equations of motion is the equations of motion are well. What should I say? You can think of if you're a classical physicist, this means nothing, because m is defined by a boundary condition on some path integral, and then we exponentiate it. So the practical way to think about it is that you lower this from the exponent, and you just resum it. So it's a complicated sum over path integrals with funny boundary conditions. And the end result, which we got through this trick, is that it leads to a mass. But if you're a classical physicist, this really means nothing. Right? That doesn't mean anything. There are no equations of motion here.
Does it mean anything on the lattice, the monopole?
The what?
The monopole, does it mean anything on the lattice?
Oh, yeah. I'm going to say a few words about it on the lattice now. Yeah.
Just to understand, what we did before is to take the Autry model, we just go to m squared low enough, and then we have the effective theory with this sigma.
Yeah.
And we say this is dual to Maxwell.
Yeah.
But what about this quality when we have...
No, we haven't. I haven't got that. You're jumping far ahead. I'm now doing a very deep and detailed analysis of the superfluid phase.
Yeah, indeed, but what happens...
But I will discuss what happens at the phase transition soon. This is just a very deep and detailed analysis of the superfluid phase. That I'm trying to convince you that you can think about it as a U1 gauge field. And I even told you more. I told you that you can break the superfluid symmetry by adding monopole operators, which look like a cosine for sigma, which will break the superfluid symmetry. That's like a magnetic field in the superfluid. And that leads to a mass. So this is a very natural mechanism to make the photon massive. In this model, there is one pseudoscalar degree of freedom, one pseudoscalar degree of freedom. So the funny thing about it is that it makes the photon massive, but what is the spin of the photon? What is the mass of this? What is the spin of this massive photon? You can read the answer from the sigma variables. 0. It's something bizarre, right? You start from a photon. Of course, a photon has only one polarization. Then you make it massive, and instead of having spin 1, it's a spin 0 photon. It's a spin 0 massive photon. It's a 2 plus 1 dimensional thing. There is no such thing in 3 plus 1. So we have a massive spin 0 photon after adding these monopole operators. Now, I want to make some comment about the lattice. If you like lattice constructions, it's extremely hard to preserve U1 magnetic on the lattice. That's a rule of thumb. Basically any lattice model that you would write would not have U1 magnetic. So just U1 magnetic is extremely hard, if not impossible, to preserve on the lattice. The reason is that the U1 magnetic has to do with the Bianchi identity. And the Bianchi identity is extremely hard to preserve on the lattice. So therefore, any lattice constructions will automatically generate monopole operators. So most lattice constructions will basically automatically generate these monopole operators. So it's extremely hard to write a lattice model which gives a massless U1 gauge field, because these monopole operators typically are generated. And this is the famous, perhaps you heard, Polyakov's U1 confinement mechanism. There is a paper that Polyakov wrote about it many years ago. This is Polyakov's U1 confinement in 2 plus 1 dimension. Well, what Polyakov wrote is that the lattice model that he constructed didn't have magnetic symmetry, so the monopoles were generated, so the photon became massive. And he interpreted the fact that the photon became massive as confinement, because there is no more Coulomb phase. You're not in a Coulomb phase, but you're in a Yukawa phase, and in a Yukawa phase, the electric charges are confined. I want to explain now. I'll take 2 minutes to explain why Polyakov called it confinement. That might not seem obvious. What you've seen from the sigma variables is that some massive spin 0 particle, but what does it have to do with confinement? So I want to spend 2 minutes explaining why we call it confinement, and then we'll move on. So remember that we discussed introducing electric charges into Maxwell. So when we introduce an electric charge into Maxwell, let's say this is time, and we have a static electric charge. So we have a static electric charge, and we introduce it into Maxwell with no monopole operators. So that leads to an electric field, which goes like 1 over r. And there is this logarithmic potential. So there is some kind of slight confinement, but it's not linear. It's not linear confinement. It's not like the confinement in QCD. It's some slight 2 plus 1 dimensional confinement. You can ask, what is the response of the theory to putting an electric charge in the presence of monopole operators? So what happens if we add monopole operators? This might appear like a hard question. How are we going to find the electric field in the presence of these monopole operators in the action? So again, the trick is to go to the sigma variables. In the sigma variables, it becomes very intuitive. What is an electric particle in the sigma variables? I said the answer a few minutes ago. What is the dual of an electric charge in the sigma variables? Vortex. Very good. So we have a superfluid vortex, right? Imagine a superfluid vortex. But now, so the sigma runs around from 0 to 2 pi, right? And let's say that there is an anti-vortex here. So this is how the sigma variables think about electric charges. They think about them as superfluid vortices. And in the ordinary situation, where the action is just d sigma squared, we argued that the force is logarithmic. Sorry, the energy is logarithmic. But now we added the cosine. And the cosine makes a huge difference at long enough distances. Let me explain why. The cosine basically wants sigma to be pi. The cosine doesn't like that sigma is away from the minimum. So actually, in most places, sigma doesn't change very much. Previously, sigma changed more or less uniformly in the angular variable from 0 to 2 pi. But now this is not advantageous. Sigma prefers to jump quickly from 0 to 2 pi over a very small region so that it doesn't spend a lot of time away from the minimum. So now instead of this nice picture, we have a string. We have a thin tube, and sigma jumps from 0 to 2 pi quickly. Sorry, from pi, the minimum is at pi, right? So it jumps from pi to 3 pi quickly inside this tube. So all the sigma variation is now locked inside the tube instead of a nice isotropic looking superfluid configuration. Because it's not advantageous for sigma to be away from pi everywhere in space. So it wants to lock the region where it's away from pi to a small tube. Okay? And this tube is exactly the confining string in QCD. So this actually leads to an energy that goes linearly in the distance, not logarithmically. And the force is constant, a constant attractive force. And that's exactly how confinement works in 3+1 dimensions. So Polyakov interpreted this phenomenon that the gauge field becomes a massive scalar, a massive spin zero scalar, as creating a flux tube, because that's what it does to the vortex superfluids. And the energy becomes now linear instead of logarithmic. So the conclusion is that when you have these monopole operators in the action, the response of the theory to a static electric charge is not electric field that goes like 1 over r. Rather, the electric field is constant. So there is now a charge gives constant electric field in space. And that's why there is linear confinement. So it's a drastic change at long distances, very drastic change at long distances to the response of a scalar. Okay, so this gives you some overview of this subject, of the superfluid phase. These are all facts about the superfluid phase with monopole operators. We'll continue after the break. Okay. So there was one question over the break that that's quite interesting, which is that here, to get this energy estimate, that the energy goes linearly in the distance, it's very important to understand that the width of this string does not change as you change L. Because if the width were to change, maybe the formula for the energy would be different. So it's actually a very cute exercise in classical physics. You just need to understand what happens when there are two superfluid vortices, and the equations of motion are derived from this action. You can try to prove that this width is actually constant asymptotically, and you can compute the width analytically. You can compute it basically. You can reduce everything to one integral, and which I think is computable. So you can actually prove it at home that this is true. It's a classical physics exercise. Okay, so now let's get back to the O2 model. And the most interesting question is, how do we go beyond the superfluid phase? Does the gauge theory description have any right to exist also in the insulating phase? That's the question, right? So let's review. If there are any more questions, can you ask them now? Yeah?
Monopole operator are something similar to solitons in this case. Is there any link between solitons?
The terminology usually in quantum field theory is that solitons are finite energy configurations that are made out, that they exist in the spectrum. And here, when you discuss monopole operators, you create an artificial singularity which looks like a magnetic monopole. But this magnetic monopole is not part of the spectrum. In fact, you remove this point from space, as you remember. So you should think about it as if this magnetic monopole has infinite mass, so to speak. So these magnetic monopoles that sit inside these little infinitesimal spheres are not part of the theory. They're just auxiliary objects that we use to define correlation functions of the monopole operators.
So they are not like in any sense some degrees of freedom with the
No. But, well, long story short is that you could start from a lattice model. In a lattice model, these monopoles would actually have finite mass. But from the low energy point of view, they seem infinitely massive. So there are actually physical excitations that could be viewed as these points. Yeah. What was the second question?
no.
Okay, yep. Yep.
Yeah, between the sigma variables is this sine Gordon right?
In 2+1.
And in that theory, we have a certain solution.
You're talking about 1+1. Here it's in 2+1.
So also the solution is not small.
Actually, this is the soliton. What you would call the kink
Yes.
in 1+1 becomes the flux tube in 2+1. So when I told you that you could compute its width, it's basically the same equation as the size of the kink in the 1+1 dimensional sine Gordon model. So that it's an analytically solvable exercise.
But then we don't have access to the electromagnetic counterpart. There is no excitation which corresponds to the soliton in the...
Oh, there is the flux tube. This is the flux tube. Yeah. This is the confining flux tube of the U1 gauge theory with monopole operators. Any other questions? Okay. So let me review the O2 model. We did a lot of work on the superfluid phase. So this is the CFT. This is the superfluid phase, which we now argued is dual to F squared. So we have a nice dual description deep in the superfluid phase. Here there is a single gapped trivial vacuum. Gapped trivial vacuum. So this is dual to F mu squared. Then we also argue that e to the I sigma is dual to what? Monopole operator. And the conserved superfluid current is dual to epsilon mu nu rho F nu rho. That's the U1 magnetic symmetry. So we have a nice duality. We could deform the O2 model by some magnetic fields that would look like a cosine, but I don't want to do that. I want to preserve the U1 here. So we preserve the O2, so it's not confining. This is a Coulomb phase. So here the charges have Coulomb interactions. There is no confinement of the charges. Oh, and furthermore, we also said that superfluid vortices are dual to point charges, point probe electric charges. Okay, so we established this very nice dictionary on this part of the phase diagram. And as I said, we could add some magnetic fields to break the O2 symmetry, and then there will be some confinement, and you could make the story a little bit more elaborate. But the big question is, how do we continue past this point? If we have a gauge field, how do we pass this phase transition? And the answer is that we have to add matter. So it turns out that there is a way to do that. So there is a full-fledged duality. And duality without supersymmetry in 2+1 dimensions. It's called particle-vortex duality. The reason that it's called particle-vortex duality is exactly that. That vortices here map to particles here. And soon we will see that also the opposite is true. That there are going to be particles, vortices on this side, and they will map to particles on this side. We'll see it in a moment. So there is a duality, which is a non-supersymmetric 2+1 dimensional duality, which is surprising. It's called particle-vortex duality. And the idea of this duality is that this gauge field theory description can be extended to the whole phase diagram if we add some matter fields. So let's write the Lagrangian. So the Lagrangian has the gauge field piece. And I'm not going to add monopole operators. You could deform this duality by monopole operators, but I'm not going to do it for now. And then you add some matter fields. And the matter fields are charged scalar fields with some mass and some quartic. And I'm putting the coefficient of the quartic to 1 for the reasons that I explained in detail in the first lecture, that it would flow to whatever it needs to flow at long distances. So let's analyze the phase diagram of this model as a function of m squared. Well, let me just call this m twiddle squared, not to confuse with the previous m squared. So we can do an analysis of this model, very much like we did before, but now it's a gauge theory with matter. Sometimes people write it in shorthand notation, U1 plus 5. This 0 stands for something that I'll explain later. It has to do with Chern-Simon stuff. But people write this model just in shorthand notation, like U1, 0 plus 5. That's it. It's a shorthand notation for this whole Lagrangian. So let's analyze it as a function of m twiddle squared, again with the help of the audience. So at huge positive m twiddle squared, what do we get? Oh, let's start before. What are the symmetries of this model? What are the global symmetries? Which U1? What are the global symmetries? Yeah, there is only U1 magnetic. The only symmetry of this model is U1 magnetic, which has to do with the conservation of the following current. The current is given by epsilon mu rho, f mu rho, and there is some 2 pi usually. And that's the magnetic current. That's the only global symmetry. The symmetry that takes phi to e to the I alpha phi is not a global symmetry, it's gauged. Okay? That's the only global symmetry. That's SO2, right? This is the same as SO2, while our previous model, the superfluid model, actually has O2. So there is a slight disagreement. And this disagreement is resolved if you realize that there is also charge conjugation symmetry. So there is also a discrete charge conjugation symmetry, which combines with SO2 to O2. That's a small fine print that would not be important for the lecture. So the only global symmetry is U1 magnetic. So what happens at huge m twiddle squared? What is the low energy physics? Huge positive m twiddle squared. Just a massless gauge field. The effective field theory is f mu squared. What is the fate of U1 magnetic? Is it broken or unbroken? Well, let's recall this discussion. Is the U1 magnetic broken or unbroken in this phase? There is it's dual to a Nambu-Goldstone boson, so it must be broken. Yeah. It's because the expectation value of the exponent is non-zero. It's an exponent, so its expectation value is 1. There's a circle of vacua here. Pure electromagnetism has a circle of vacua, which are given by the sigma expectation values, and they're the same as the monopole expectation values. So the monopole actually condenses in this vacuum. It's U1 magnetic is spontaneously broken. So U1 magnetic is spontaneously broken. There is an S1, a Nambu-Goldstone boson, and we can write it as d sigma squared. So it's the same as d sigma squared. I have not emphasized this point, but I should maybe say it now, in a more pronounced way, that in the phase of Maxwell's Coulomb phase, without the magnetic monopole operators in the action, it's equivalent to a compact scalar field, and this is a Nambu-Goldstone boson. So it's the same as saying that the monopole operators of Maxwell field theory have non-zero expectation values in the vacuum of the Coulomb phase. So these expectation values are non-zero in the Coulomb phase. So the U1 magnetic symmetry of Maxwell's theory is spontaneously broken in the vacuum. People call it monopole condensation. Monopole proliferation is when you add the monopoles to the action. Monopole condensation is when they condense in the vacuum. So we can add here monopole condensation. Not proliferation. We don't add monopoles here to the action. We just condense them. So that's one phase of the model. There is a circle of vacua. Right? So we have this picture. Then what happens at huge negative M twiddle squared? Somebody answered this question before. When asked about the superfluid phase. What happens at huge negative M twiddle squared? Yeah, this is where this is Higgs mechanism now. So how many vacua are there now? How many vacua? One. Trivial and gap. So there must be a phase transition. And it looks very much like this phase diagram. One side is trivial and gapped, one side has a circle. And we already established the dictionary on this side of the circle. So maybe they are the same. So the claim is that this CFT is actually the same as the O2 Wilson-Fisher CFT. It's dual. So we write like U1 plus phi is dual to phi. Okay? It's a duality in 2 plus 1 dimensions. These two models, albeit being very different, having a completely different number of degrees of freedom, they are the same at long distances. Let me explain more about how that works. I'll just put them upstairs here. I'm not claiming that these models are exactly the same. They only are the same at long distances. This is a very important point. The phase transition is the same and the phases are the same. But they're not the same. It's not like there's a change of variables between one and the other. It's only the long distance limits are the same. Okay, there are many things to explain now about the interpretation of this duality. But before I go into the interpretation, I wanted to discuss a little bit the trivial gapped phase, because we did a lot of work on the superfluid phase, but I didn't say much about the trivial gapped phase. I want to say a few words about it because it's very important in order for you to understand why this is called particle vortex duality. So let's look at the trivial gapped phase from the O2 model point of view. In that case, phi does not condense. There's a single massive vacuum, and the excitation is phi. We have a massive excitation phi. This is a particle excitation. Now, let's compare that with the trivial gapped phase of the gauge theory. In the gauge theory, I should have called that phi hat. That's a very bad notation on my part because this is a different phi. This phi had nothing to do with that phi. So I should write here like this. Oh, and another thing that I should write before going back is that you see that the diagram is reversed. So it's not like, so the duality is implemented by a reversal of the diagram. That means that m squared is mapped to minus m squared. Or in operator language, that means that phi squared is mapped to minus phi hat squared. And that may look shocking. Phi squared is positive. How can phi squared under duality go to something that's negative, definite? And what's the answer to that? Does anybody have an idea? How can it be that phi squared goes to minus phi twiddle squared? Or phi hat squared? How is this possible? That something that's positive definite is mapped under duality to something that's negative definite? Because these are composite operators. In quantum field theory, composite operators have no inherent positivity or negativity. Okay? Okay, so let's discuss in a little bit more detail the trivial gapped phase from the gauge theory point of view. So phi hat condenses, and we have a Higgs mechanism. and we have a Higgs mechanism. How does a Higgs mechanism work? We write phi hat as the norm of phi hat times the phase. Times the phase, right? We do that all the time in the Higgs mechanism story. And remember, I hope this is not confusing, but in this model we discussed these vortices in which the phase winded around with angle 2 pi. What if we try to discuss the same in this model? Hopefully that would not be confusing. So now sigma hat goes to sigma hat plus 2 pi. In the O2 model, this was relevant in the superfluid phase, where there was an Ambu-Goldstone boson. But in the gauge theory, this is a relevant question to ask in the Higgs phase. Because in the Higgs phase, it's the trivial phase. That's where sigma comes to life, because phi condenses. Okay? So previously, we argued that this costs infinite energy because of this infrared divergence, the logarithmic infrared divergence. But now this is not true, because there is a gauge field. So where is the difference? The difference is that when we compute the energy, previously we had this sigma hat squared, and this just diverged. D2x, and this just diverged because of the angular variable in the angular derivative. But now this is not true because there is a gauge field. So now the kinetic term is it's d sigma hat plus A. And now there is a potential that maybe this configuration will have finite energy because we can use AI to cancel the gradients. So indeed, the most important gradient is the theta gradient, right? So let's estimate it. So this is R dr, and then we have a gradient with respect to theta of sigma hat, d theta sigma hat, and then we have the gauge field in the theta direction. And we said previously, there is an R squared here. So there is 1 over R, and there is 1 over R here, and this is squared. So previously, we said that this is order 1 because it just winds around the circle, and then you take the second power, and this logarithmically diverges. But now we can cancel this off. We just take A theta to be basically minus d theta of sigma hat. So we can cancel this off. And we have finite energy asymptotically. Incidentally, when you're careful about these factors of R, this leads to some magnetic field. So actually this leads to some FR theta, which is non-zero. So the gauge field, so basically there is a magnetic field in the gauge field that cancels off the energy in the superfluid vortex. So in a Higgs phase, these vortices actually exist. They have finite mass, and they're actual part of the Hilbert space. And in fact, these are the simplest excitation of the theory. These are some of the simplest excitations of the theory in the Higgs phase. Another simple excitation is just the W boson. That's another familiar excitation in the Higgs phase. It's just the W boson, right? But this is another interesting excitation. And this excitation is particularly interesting because this excitation is charged under U1 magnetic. So this is charged because it has this magnetic. I told you that this leads to a magnetic flux, and you can prove that the total magnetic flux is 2 pi. So this is the simplest excitation that carries magnetic U1. So this is charged under the U1. And therefore, this is the dual of this phi excitation. So now we have an even more extended dictionary, which is that in the Higgs phase, or the trivially gapped phase, the phi excitations in the superfluid and the phi excitations in the O2 model map to magnetic vortices, which have finite energy or finite mass in the gauge theory side. So we have a very elaborate map. In this side of the duality, we have phi on one side, and this is dual to these vortices. But these are But these are now the good vortices. So let's call them good and bad vortices. These are the good vortices that have finite energy or mass, and they carry well-defined U1 magnetic charges. These vortices are the bad vortices because they don't have finite energy, and they map to something that doesn't have finite energy on the other side. Yep.
This construction is somewhat similar to the top point of.
Yeah, it's exactly the same. It's the same idea.
But is it naturally also by, I don't know,
Yeah, it's related in some way. I can explain later if you want, but it's related in some way. If you want to take away a message from this story is that remember plus one dimensions. When there is a Higgs mechanism, there are finite mass vortices, magnetic vortices. They're called. They're called magnetic vortices because you need to use a gauge field to cancel off this infinite energy, and then the gauge field induces magnetic flux, and you have total magnetic flux through the plane. You have 2 pi magnetic flux through the plane. So people think about these particles are just like little solenoids. So that's a common picture to see, is that you think about these charged particles under the magnetic symmetry as little solenoids that can move in space. They have finite mass. So there is a way to make the superfluid vortices good, which is to gauge the U1 and then attach the magnetic field that cancels off the infinite energy. And these are dual to the phi excitations in the gapped phase. So you see that there is a very elaborate dictionary that these theories look very different. One has a gauge field plus a complex scalar, one has just a complex scalar, but they have exactly the same phases, and people have shown that they have the same phase transition, the exact same conformal field theory. So it's a very elaborate and impressive duality. On one side you have particle number symmetry, on the other side you have magnetic U1 symmetry, and there is a very elaborate mapping of the excitations, of the symmetries, of the qualitative, even some features that don't really make sense mapped nicely, like these bad vortices. So it's a very cute example of duality in 2 plus 1 dimensions without supersymmetry.
So, and for example, the W boson to whom map?
Well, you see, this object is somewhat easy to map because you're in a phase where the U1 You're in a phase where the U1 magnetic symmetry or the superfluid O2 symmetry is unbroken. So some particles in the Hilbert space carry SO2 quantum numbers. So it's natural to ask what is the simplest object that carries this on that side and carries that on the other side. The W boson is a spin 1 particle, but it carries no symmetries. So it's very hard to map. This duality has never been proven. Nobody showed that there is a 1-to-1 mapping between the resonances. But everybody believes that this duality is correct. However, this duality, I should explain what this means, what the word duality means. It's a very important notion that we use in high energy physics all the time. So, can it really be that this model, let's call it the phi model, and the U1 plus phi hat model, can it really be that these models are just exactly the same, that they have the same spectrum, and that there is a mapping between all the particles? It cannot be true, because at very high energies, this has 2 degrees of freedom and this has 3. These models are definitely not the same. They're not the same. So what does it mean when we say duality? In particle physics, when we say duality, what we oftentimes mean is infrared duality. What is infrared duality? Infrared duality means that they have the same phases and the same phase transitions. So both models have a diagram like that with a fixed point. And you remember that they were reversed. So in one it was like this, in one it was like this. In the mapping between the 2 theories, there is a reversal of m squared. So when we say infrared duality, we don't mean that the models are exactly the same. What we mean is that some neighborhood of the phase transition is the same. So we take m squared on the phi side, we dilate so that we're very close to the phase transition. We take m twiddle squared or m hat squared on this side, we dilate so that we're close to that phase transition. And in that neighborhood, all the physical questions should agree, including the particle spectrum, all this stuff. In that neighborhood, however, it's very hard to compute because you're near a phase transition, everything is strongly coupled. And we can only do, so if you think about it deeply, all the stuff that I've shown you is qualitative matching. I never computed the mass of a particle to like 10 digits and showed you that it's the same on the other side. Nobody can do that. But we can show that qualitatively the models seem very similar. They have the same type of excitations. Everything seems to work, so maybe they're the same at long distances. And then it's up for the lattice or experiment to prove that this is really the case. And in this case, it was done. So it's a rare example where we know it's actually true and it's proven on the lattice that it's in very good shape. The other dualities that I'll show you are not in such a good, do not have so much evidence in their favor as much as this one. Any other questions? Yes?
But if you go instead in the very massive limit,
Yeah.
you can also find the matching from the topological factor.
Well,
All the theory,
all the questions about the deep infrared would agree. But if you try to compare the mass of the simplest particle, it would definitely disagree. Let me show you why. I mean, the spectrum of particles does not agree very far on this die. If you compare the spectrum here to the spectrum here, it's definitely not the same. It's easy to see. The models, they agree qualitatively. They have the same topological phases. They have the same like long distance behavior. But if you actually compare anything that has mass, then it doesn't work. But near this phase transition is supposed to work. That's why it's called an infrared duality. It only works near the phase transition at long distances. Seiberg duality, which I assume you learned about from Napadol, is exactly on the same footing. And I assume that Napadol explained it. That it's not an exact equivalence, it's only a long distance equivalence near some phase transition where there are massless Coulomb fields. So many dualities that we know about are of this sort. Any questions before we move on? Any last questions about this model? I'm not going to start a new subject now, so I'm in a tight bind now. I'll just tell you where we move on next. Yes.
In this boson Hubbard model that you were discussing, should you think of these two terms as kinetic terms and potential terms?
Yeah, because one of them leads to a hopping of the bosons and the other to a potential for the bosons not to clump together.
Is there a sense of relevant operator and irrelevant operator?
Well, you can try to go close to the phase transitions and do that, yeah. People have done such exercises. You're asking how to go to a continuum limit from the Hubbard model?
Because it seems like on the lattice you have a lot more freedom to form of these.
Yeah, it's like I told you, it's like discrete mathematics versus calculus. On the lattice you can do whatever you want. You could write 100 different other terms. But near the phase transition, everything becomes beautiful and continuous, and it's extremely limited. So it's the O2 Wilson-Fisher model. There are only two relevant operators, which preserve the symmetries, and everything is completely fixed by continuum considerations. So the lattice is very messy, but when it has a continuum limit, it's extremely constrained. That's the message. Yes?
On the other side, when m squared is very big, we need to add matter to restore the equality. What we did before, we just say that u1 plus phi hat is equals to 2 to the 5, is what we said.
Yes.
So I don't see why we should. Is there any kind of motivation for doing this? So who came up with this idea? And okay, a posteriori it works. Okay, so we have this map.
Oh, there is no systematic way to find these things.
There is no kind of scale in the effective theory on the other side.
No, nobody can. First of all, nobody can derive this equivalence in the continuum, and secondly, it's a guesswork. You guess something, you check everything you can check. It works. You declare victory and you write a paper. 99% of the time doesn't work. You find some mistake and then you don't write a paper, or something you do. Yeah. No, it's complete guesswork. Nobody has come up with a systematic understanding of how to arrive at these things. I should, however, say that you will see in the course of the next 2 lectures that there are more examples of this, and you can think about them as somehow interconnected. So if you assume one, you can sometimes derive the other. You can never derive all of them, but you can say, if I assume this and that, I can derive this. So there is some interconnectedness in the space of ideas. It's called the duality web, because they're connected by some logical chains, which are complicated. There is one, because I have 5 minutes and I don't want to start a new subject, I want to say something that might be of interest to some of you. It's a more advanced thing than I want to talk about. I'm kind of a little bit wondering if to get into that or not. I'll just mention it as a cursor. There are some students that maybe know all of that, so this is for the advanced students, okay? So if you don't understand what I'm talking about, ignore it. That's maybe just for the more advanced students, it's a very important thing to know. So there is something that I was a little bit careless about, which is that the gauge, it's not only that the gauge theory model and the scalar model are not the same. They even have different number of degrees of freedom, but also the number of couplings is not the same. So here I omitted the quartic coupling, but I kept the gauge coupling. And in fact, if you think about the gauge theory model, so this is the U1 plus phi model, you should think about it as a function of the gauge coupling and the quartic coupling. So there is a complicated RG kind of diagram in the space of G and lambda. And what is known to be true is that there is essentially a special line here. In this part of the phase diagram, it flows to the O2 fixed point, and it's dual to the phi model. So what I explained to you is essentially true about this part of the phase diagram. It's true at sufficiently weak gauge coupling. But in this part of the phase diagram, the transition is not second order. It's actually first order. You see? When you have 2 phases, like here, there is a superfluid phase and there is an insulator phase. It doesn't have to be true that the transition is a single second order transition. It might be a first order transition, where the 2 vacua just play each other like that, as in any first order transition. And this example is probably the simplest one that realizes this. So for sufficiently large gauge coupling, the transition is first order. It's not second order. And therefore, there is no sense of infrared duality. Infrared duality is about long distance physics. If there is no gapless matter, like a conformal filter is second order transition, there is no sense of talking about infrared duality. So there is no duality here. However, something very interesting happens on this line. Oh, and in condensed matter, this is called type 1 superconductor. And this is called type 2 superconductor, this parts of the phase diagram. There is a very interesting thing to say about this line. So this is the comment for the more advanced students. On this line, you are somehow in between, but it's still second order. However, you need to jump from second order to first order. So it cannot be the same second order model as this one. So in fact, on this line, you find something that's called a multicritical. A multicritical point. So this is a special conformal filter in which the phi to the 4 is tuned to 0. And the model is given, so there is a duality here. But the duality is not to phi to the 4 model. The duality is phi to the 6. It's to the phi to the 6. So it's a special conformal filter where you tune the phi to the 4 to vanish by hand. And then you just flow with phi to the 6.
Isn't phi to the 6 marginally irrelevant?
Yes. So this, in the long distance limit, this actually flows to mean filter. So here you get non-trivial scaling exponents that were measured. Here you get mean filter exponents. And then you get first order transition. So what I wanted to say for the more advanced student is that there is this line where the dual description is actually a multicritical point, which is mean field theory, and not the phi to the 4 model. And then you go to a first order transition. So that's what I wanted to say. Probably it's a little bit too much for some of you, but maybe for others it's not. Okay, thanks. No, that's it, yeah.